Welcome back to the Deep Dive. Today, we are peering deep into a transformation that honestly goes so far beyond just swapping gas pumps for charging plugs. We are looking at a foundational shift. A complete restructuring of our energy and transportation ecosystems all at once.
It's not just about new cars. Not even close.
Exactly. It's about strategically merging the vehicles themselves, the power grid, smart roads, and the cloud itself into one colossal integrated system.
That's absolutely right. And look, if you want to understand what a 21st century economic restructuring really looks like, you have to analyze a document like this one.
So let's get into it. Our deep dive today is into the strategic technology roadmap for vehicle energy interaction and infrastructure.
And we're going to tackle this using a consultancy lens. We'll evaluate the current status, identify the critical bottlenecks, and then map out the really ambitious goals that drive this blueprint right up to 2040.
Okay, so let's unpack the sheer strategic significance here. Why are we paying such close attention to this specific roadmap? Because the economic commitment required to make this all happen is, it's just staggering.
It really is.
We're looking at the foundational investment needed just for the charging and swapping infrastructure, and that's before you even get to the massive grid upgrades needed to support this electrifying vehicle fleet.
Right. And that combined need for just the infrastructure is expected to hit about 1.5 trillion Chinese yuan by 2030.
1.5 trillion.
That's the direct cost, the price tag for getting the system built and stabilized over just the next 6 years. But, focusing only on that cost completely misses the strategic point.
Indeed. The true measure of scale here is the secondary economic effect, the stimulus. We're talking about this infrastructure investment potentially stimulating, 24 trillion CNY in related consumption across the entire economy.
24 trillion. It's a massive figure. To give you some context, that's roughly equivalent to the entire annual GDP of a large G7 nation.
So this isn't just an infrastructure project.
No, it's a profound economic stimulus strategy. That investment targets the highest value manufacturing sectors. We're talking power electronics, specialized materials for things like liquid cooling, advanced battery manufacturing, construction. It propels a massive news cycle of a low-carbon economy and green consumption.
So we're not just building charging stations. We are, in effect, laying an essential economic pillar for the widespread adoption of new energy vehicles, or NEVs, and basically engineering a new green industrial revolution.
Precisely. This shift is the deep continuation of the electrification revolution, but with a really critical difference.
Okay.
We are transitioning transportation from fossil fuels to clean, and this is the key word, controllable power. And the infrastructure itself has a dual role. The first role, the obvious one, is providing that seamless charging and swapping convenience.
And the second role, that's the game changer, the one that makes that 1.5 trillion investment actually worthwhile.
That's the revolutionary part. It's enabling a two-way flow of energy and information, V2G or vehicle to grid. This vision transforms the massive fleet of EV batteries from, passive energy consumers that just stress the grid.
Right, everyone plugging in at 6 p.m.
Exactly. It turns them into flexible, controllable resources for the new power grid system. They become prosumers, consuming when energy is cheap and plentiful, and providing power back during peak demand.
So our mission today is to assess the progress of the first phase of this. That's RoadMap 2.0, to really understand what worked and maybe more importantly, what didn't.
Right. And only then can we really appreciate the magnitude of the technological leaps that are required to hit that 2040 vision.
All right, let's start with that status check. Looking back at the performance of the previous roadmap, RoadMap 2.0, in terms of sheer scale, the results are pretty spectacular. The speed of deployment exceeded nearly all expectations.
Oh, the hardware deployment has been truly historic. This pace really solidified charging infrastructure as a core engine of NEV growth. It laid the foundation for mass adoption, and it proved that when the policy is right, you can build immense capacity extremely, extremely quickly.
Okay, let's get into some of those success metrics. This is as of late 2024. For fast charging ports, the original goal for 2025 was 800,000 DC ports. Where are we now?
We have more than doubled that goal, and we did it early. We're at 1.643 million deployed DC charging ports.
Wow.
This incredible overshoot in just physical capacity is exactly what you need to do to alleviate that consumer range anxiety and really drive market acceptance.
And it seems the power capability, the actual, the juice, has matured even faster than anyone anticipated.
Absolutely. RoadMap was targeting 750 volts as the mainstream platform, but in practice, 750 V to 1000 V is now basically standard, which enables much quicker charging times. And on top of that, the maximum charging current is already at 800 amps or higher. That just blows past the conservative 400 amp target set for this phase. It really speaks to the rapid innovation in power electronics, and especially in thermal management.
We also saw phenomenal results in the speed of physical battery exchange. The swapping time for passenger vehicles was targeted at, 5 to 7 minutes?
And that has been efficiently reduced down to just 3 to 5 minutes. So you're matching the speed of fossil fuel refueling. For the consumer, the time penalty is gone.
And this is happening for heavy trucks as well.
Yes, and we're seeing heavy-duty truck swapping mature very quickly, too. There are over 1,000 heavy-duty truck swapping stations already built, and that's solving the high-volume, short-haul logistics problem in centralized areas like ports and mines.
The numbers are just irrefutable. The total network size reached 12.818 million units by the end of this year. We have, without question, built the world's largest electric vehicle support network.
No question.
So, we've built the highways, we've built the filling stations. Now for the crucial question. If the hardware success is so vast, where do the strategic bottlenecks emerge?
This is the key question. If we connect this to the bigger picture, the challenge now is transitioning from quantity to quality.
Right.
We've successfully built the plumbing, but the intelligent control system that actually manages the flow, it's lagging. And this delay reveals two critical systemic bottlenecks that are preventing us from achieving the full efficiency and strategic goals of that 2025 plan.
Okay, let's start with the first one. Ordered charging, or V1G. This is the basic level of intelligence, right? Just making sure we charge when the grid has excess capacity.
The very first step.
The sources indicate coverage is only around 50 to 65%. That's barely meeting the low end of the goal. Why the lag?
The hurdle is multifaceted. It's physical, it's economic, and it's behavioral. V1G requires the charger to communicate with the utility system and delay charging until off-peak hours.
And it does that using time of use tariffs, right?
Yeah.
Cheaper electricity at 2 a.m.
Exactly, that's the incentive. But the physical barrier is often in older residential areas. The grid capacity there, specifically the local transformers, they just weren't designed for thousands of EVs plugging in simultaneously after 5 p.m.
So the local grid just can't handle it.
It can't. You need massive and costly grid upgrades just to handle the potential localized demand spikes. That's a huge physical and financial barrier.
I understand the physical constraint. But if the grid benefits so much from preventing that peak demand, why haven't strong, standardized time-of-use tariffs been mandated across the board? Isn't the benefit to the utility enough of an incentive to push it through?
That's an excellent point, and it really highlights the policy gap. The implementation of strong, economically attractive tow-you tariffs has been, well, patchy.
So the discount just isn't big enough.
It's marginal. If the discount for charging at 2 a.m. is tiny, the average user won't bother to change their behavior. They'd rather just pay the peak rate for the convenience of plugging in when they get home. So until that financial incentive is really robust, widespread user participation, which is absolutely necessary for V1G to function as a grid stability measure, it just won't materialize. It leaves the whole system functionally uneven.
That makes perfect sense. If you don't reward the behavior, you don't get the desired outcome. Now, for the second and what sounds like the most critical bottleneck, V2G commercialization. This is the holy grail of treating the car as a battery asset.
This is the most pressing strategic gap, yes. Moving from one-way charging, V1G, to this two-way interaction, V2G. And the potential impact is truly immense.
How immense?
By 2040, the aggregated EV batteries could offer a daily adjustable capacity estimated between 220 and 260 billion kilowatt hours. That is a flexibility resource that could fundamentally stabilize a power system that's reliant on intermittent solar and wind.
Yet the actual deployment of V2G-capable piles is a tiny fraction of the goal. The target was 100,000 vehicles deployed in V2G projects. The reality is around 10,000. Why such a monumental miss on this core strategic goal?
The problem isn't the battery. It's not the car. It's the lack of a standardized, secure information channel. You have three key components: the vehicle's battery management system, the charging pile, and the utility grid's dispatch system, and they haven't been fully harmonized.
They don't speak the same language.
There is no universally agreed upon language or protocol for the pile to confidently say, I have 50 kilowatts to send back to you now, and for the utility to accept that command reliably and safely.
And the missing commercial model you mentioned before.
Yes, the commercial layer. Even if the technology were perfectly harmonized today, who pays the vehicle owner? How is that payment audited, standardized, and compensated?
Right. How do you get paid for letting the grid use your battery?
Exactly. You need top-level design documents and pilot programs to validate precisely how utilities compensate the owner for, degrading their battery slightly, how safety is guaranteed during discharge, and how all that data is handled securely. Until the market compensates these resources fairly and seamlessly, V2G just remains a vast untapped technical potential, not a commercial reality. And the next roadmap phase is entirely dedicated to solving this V2G failure.
So to summarize part one, using our transport analogy, we've built the best, fastest electric superhighways in the world, and the cars can go faster than ever. But the traffic control system, V1G, is only half functional, and the automated toll booth structure, the V2G commercial model for smooth, smart, two-way energy traffic, it's barely in existence.
It's perfect summary.
The next phase, then, is all about solving that control and commercial problem while at the same time pushing the hardware to even newer extremes. So if the software and the policy are lagging in V2G, let's look at the hardware, because it's certainly not slowing down. Yeah. The strategy for this next phase pivots sharply to 4 key technological domains that are driving for low carbon, extreme speed, and intelligent infrastructure.
That's right.
And we start by tackling the pure power requirements with intelligent charging, focusing on something called megawatt ultracharging, or MCS.
The ultracharging trend is a global race for sure, but the data clearly shows a massive acceleration here. While foreign systems, like those that adhere to the CCS standard in the EU and the US, they typically target around 350 kilowatts.
Which is already pretty fast.
Very fast. But domestic development is pushing far, far beyond that. We've already deployed over 3,000 ultracharging stations and nearly 100,000 ultra-fast charging piles as of late 2024.
Now, this sounds like a technology that's primarily designed for logistics, not for passenger cars, right? I mean, the power requirements are just huge.
Right. Absolutely. While faster charging benefits everyone, the need for megawatt-level power comes directly from the heavy-duty logistics sector. And this is where the innovation really shines, because it enables the electrification of long-haul freight and heavy commercial vehicles.
Which have historically suffered from these massive batteries and painfully long charging times.
Exactly. This solves that problem.
So what are we talking about in terms of raw power output?
Well, companies like Huawei and NRI have megawatt-level systems that are already being trialed in closed environments, particularly in places like mining sites and ports, where standardized routes make deployment a lot easier.
And the numbers.
Huawei's system, for example, outputs 1.44 megawatts. That's 2,400 amps.
Okay, to put 1.44 megawatts in perspective, that's roughly enough continuous power to run about 150 standard homes simultaneously.
All being pumped through a single cable into one truck.
Yes. How do engineers even manage that level of complexity and heat safely?
This extreme power relies entirely on breakthroughs in thermal management and material science, specifically full liquid cooling. We're moving beyond just simply cooling the cable. We are now seeing full liquid immersed cables and charging guns.
So the components are literally bathing in coolant.
Essentially, yes. The liquid acts as a highly efficient heat sink, and it allows the conductor to carry that enormous 2,400 amp current without overheating or, risking a catastrophic failure. The goal is charging at the same frequency and speed as refueling. It's about making the 15-minute pit stop a reality for heavy logistics.
And that thermal management requirement, that also ties directly into the efficiency goals, doesn't it? I mean, losing less heat means higher efficiency.
It does. The roadmap targets core component efficiency. For example, those mainstream 30-kilowatt power modules need to reach efficiencies above 96% by 2030. This push for precision engineering and power electronics is essential not just for saving energy, but for maintaining the system's operational lifespan under these extreme conditions.
Okay, moving beyond sheer power, let's explore the more futuristic side of this, the autonomous charging future. This is where the roadmap integrates the smart vehicle side with the smart energy side.
This is truly where that concept of the vehicle energy road cloud system comes alive. The convergence of smart driving and charging leads directly to automation, and we're moving beyond simple, fixed robotic arms, which are, frankly, cumbersome and location-specific.
Right.
We're moving toward fully mobile charging robots, like those being developed by Shanghai Electric.
The sources mention human-like embodied robots. What function do they serve that a simple fixed arm cannot?
Their mobility and their high-level autonomy are the key. They are envisioned to handle complex, high-volume, standardized scenarios. Think of large fleet depots, urban hubs, or multi-story car parks where the vehicle may not park perfectly every single time.
Ah, so they can adapt.
They can adapt. They handle guidance. They physically plug in the heavy liquid-cooled cable. They manage the energy flow. And they can even conduct basic station inspection. This fully automates the replenishment process. It removes the human element entirely from the physical transaction.
And the other side of automation is wireless charging maturity. For years, this felt like pure science fiction. Is it actually becoming viable for high power?
It's transitioning very rapidly from just demonstration to actual product development. We've seen some impressive international testing. RNL and VW demonstrated 270 kilowatts, which shows that high power is absolutely feasible.
And what's available now?
Domestically, there are already products that offer 11 kilowatts at 92% efficiency, and the targets are ambitious, reaching 22 kilowatts at 94% efficiency and driving the cost down dramatically below 600 CNY per kilowatt by 2035. That would make it competitive with basic wired installations.
So you're eliminating the last hassle of charging the plug itself.
Ex-
But for all of this automation, the robot guidance, or the wireless coupling, to work reliably in a crowded urban environment, the system needs absolute precision. We need to talk about supporting architecture, this sensing communication parking control system.
This is the brain of the automated system. It requires the charging network to be fully integrated with next-generation communication technologies, 5G, 6G, and also ultra-wideband, or UWB, technology. This is crucial for precise localization and for identity authentication.
What kind of precision are they targeting?
The target for localization error is less than 4 centimeters by 2040.
4 centimeters, that's less than the width of a golf ball.
It is. We are talking about aerospace levels of docking precision for a mass-market consumer product. And that precision is mandatory for the robot to align the plug safely, or for the wireless pad to couple with maximum efficiency, and for the system to reliably identify the vehicle for seamless payment processing.
Okay, so let's circle back now to the strategic failure we identified in Part 1, that V2G commercialization bottleneck.
Yeah.
The next critical domain, V2X in the virtual power plant, or VPP, is the mechanism designed to finally solve that problem.
Yes, V2X is the foundation for creating these virtual power plants using aggregated EV batteries. And VPPs are essential for the grid because they can offer peak shaving, frequency regulation, and reserve capacity. By coordinating millions of EVs, the utility can essentially tap into a distributed energy resource that is far greater than any single conventional power plant.
We mentioned that 2024 saw significant policy acceleration. What specific policy push are we seeing that will finally unblock that V2G commercialization gap?
The release of top-level design documents and, more importantly, the launch of the first batch of pilot cities, that's 9 cities, 30 projects, signifies a real move toward defining the commercial rules.
So these pilots aren't just testing the technology.
No, the tech works. They are validating the critical components needed for a sustainable market. Safe discharge regulation, formalized safety protocols, and, most importantly, the commercial models that standardize how grid operators pay the vehicle owner for the services they provide.
What is the ultimate vision for V2X integration? I see this comprehensive acronym: photovoltaic, storage, charging, swapping, and hydrogen. That sounds like you're building a local power fortress.
It is exactly that. It's the shift to autonomous microgrids at the grid edge. Instead of relying solely on the main utility grid, the charging station becomes a self-sufficient energy hub.
So the solar panels power the station.
The solar panels, or PV, power the station. The large stationary battery, the storage, stabilizes the local power supply. The EV batteries, through charging and swapping, act as flexible support. And hydrogen is there for the super heavy loads. This system enabled local green power generation, storage, and consumption loops, and it effectively solves the intermittency challenge that plagues high levels of renewable energy adoption.
This profound redefinition of the vehicle, from just a consumer to an active grid participant, also integrates it into economic mechanisms beyond just electricity trading, right?
Absolutely. In this vision, the electric vehicle transforms into a core carrier linking energy consumption, energy storage, and eventually participating directly in carbon trading markets. If your VPP is powered by certified green energy, the services you provide back to the grid can become carbon credits that can be traded. It fundamentally links the transportation sector to the broader decarbonization economy.
The strategic roadmap is clearly a dual track. The electric side is set to dominate urban mobility and grid integration. But now we have to shift to the hardcore challenges. Long-haul, heavy-duty logistics, where the strategy pivots to the hydrogen track.
This dual approach is absolutely necessary because pure electric solutions, they struggle severely with three factors that are inherent to heavy logistics.
Which are?
The need for massive range, the payload constraint that's imposed by carrying huge heavy batteries, and the demand for extremely rapid refueling. Hydrogen, with its high energy density, is the intended solution for these specific endurance pain points.
And what's fascinating here is that the foundation is already built. The sources show China already leads globally in hydrogen infrastructure quantity, with 428 refueling stations built by the end of 2023.
And critically, the economics are currently strong. Due to extensive use of industrial byproduct hydrogen, the refueling costs are remarkably low. They're averaging around 35 CNY per kilogram, which provides a significant cost advantage over most global competitors and, well, it makes the business case for hydrogen logistics viable today.
So if the deployment is strong and the cost is low, where are the key technological and infrastructure gaps on the road to maturity for that 2040 goal?
There are three critical limitations that currently restrict the use of hydrogen primarily to shorter, high-volume routes.
Okay.
First, there's the liquid hydrogen, or LH2 technology gap. Currently, the entire civilian supply chain relies on high-pressure gaseous hydrogen. Liquid hydrogen infrastructure, which is essential for true long-haul, high-capacity transport, it's virtually non-existent commercially.
What engineering hurdles make liquid hydrogen so challenging, and why is this gap considered a severe limitation?
The challenge is extreme cryogenics. Hydrogen has to be cooled to minus 253 degrees Celsius to liquefy. This requires incredibly advanced insulation, high-efficiency liquefaction plants, and specialized cryogenically stable refueling components and tanks that minimize what's called boil-off, the natural warming and evaporation of the liquid.
So just keeping it cold is a huge problem.
A massive problem. And relying only on high-pressure gas, say at 700 bar, limits the onboard density significantly. That means a truck carries less energy and has less range compared to a vehicle using LH2, which foreign competitors in the US, Germany, and Japan have already started commercializing.
The second gap, then, is about control over the manufacturing chain.
Indeed, it's the core equipment dependency. Critical, high-flow, high-pressure equipment required for rapid refueling, like the massive compressors needed to handle that 700 bar pressure, they're still primarily reliant on imports. To achieve supply chain security and autonomous control over this essential energy infrastructure, domestic manufacturing has to close this gap, and quickly.
And finally, the storage cylinders themselves. This is the third gap, and it directly impacts the weight and range of the final vehicle.
The storage cylinder technology. The current mainstream solution is the Type 3 cylinder that's a metal-lined carbon fiber wound tank. It achieves a density of 5.4 weight%.
Oh.
The future, however, lies in the Type 4 cylinders, which have a plastic liner. Our current Type 4 density sits around 6.8 weight%, so it's still catching up to the international standard of 8.0.
That brings us to the storage technology race. Let's pause and explain what that density difference, from 5.4 weight% up to the long-term target of 9.2. What does that actually mean for the payload and the cost-effectiveness of a heavy truck?
It's a huge competitive factor. I mean, weight is everything in freight logistics. If the hydrogen storage system weighs less for the same amount of energy, the truck can carry more revenue-generating payload. It's that simple.
So more cargo, less tank.
Exactly. Moving from 5.4% with Type 3 to the long-term goal of 9.2%, whether that's with advanced Type 4 or LH2, means nearly doubling the effective storage density. And that translates directly to longer range for the truck without sacrificing payload capacity. It's what will finally make zero-emission long-haul routes economically competitive with diesel.
So the technology ladder is clear. Type 3 is the current workhorse. The near-term focus is on the Type 4 cylinder, with a 2030 goal of 7.5 weight%, pushing to 9.2 weight% by 2040.
And the ultimate goal for truly extreme range and capacity is liquid hydrogen. While it's currently in the R&D and demonstration phase, its density target is greater than 9.2%. It is the essential technology to solve those endurance pain points for truly massive intercontinental high-capacity transport.
This raises an important policy question. We've seen immense success with EV battery swapping. Can that technical advantage be leveraged here? I'm talking about hydrogen swapping as a new commercial model.
The rationale is compelling, especially for heavy-duty fleets. Swapping hydrogen modules instead of the time-consuming process of high-pressure fueling would eliminate driver wait times, it would significantly reduce the initial vehicle purchase cost, and it would simplify the supply chain by reducing the need for complex, on-site, high-pressure compression at every single station.
We have the technical know-how from EV swapping. But what are the major policy and regulatory hurdles that are preventing this innovative model from being deployed widely?
This is where we see that control system lag theme resurface, but on the hydrogen side. Currently, regulatory policies mandate that hydrogen bottles must be rigidly tied to the vehicle's VIN, the vehicle identification number.
For safety tracking.
For safety and liability purposes, yes. But this rule fundamentally restricts the flexibility you need to swap standardized modules freely between trucks. Furthermore, the necessary standards and regulations for the safe road transport of these high-capacity hydrogen modules carrying compressed gas across long distances are either missing or uncertain. Without clear cross-industry policy alignment, the enormous economic potential of hydrogen swapping remains locked up.
All right, this roadmap provides a clear three-stage progression. Near term is focused on foundational connectivity and market validation. Midterm is about achieving scale and AI-driven intelligence. And the long term is about full integration and ubiquitous smart energy access. Let's chart that course and discuss the strategic meaning of these metrics.
The near-term phase, 2026 to 2030, is really focused on building that core V2G link and getting those initial commercial demonstration pilots up and running. It's all about establishing the proof of concept that V2G works reliably and crucially profitably.
So what are the concrete charging and V2G metrics for 2030 that show this foundation is being built?
The most important metric here is V2G terminal penetration. New piles installed with that bidirectional capability must reach over 10%.
That seems small.
It seems small, but that initial percentage is the critical mass you need to standardize the protocols and validate the market mechanisms we talked about. This then enables the grid to tap into an initial small capacity, a daily adjustment capability of 0.4 to 0.6 billion kilowatt hours.
And on the speed front, the consumer requirement is clear. Eliminate the time penalty of charging.
Yes. Fast charging must enable an electric vehicle to gain 300+ kilometers in 5 minutes. This metric is the direct attack on consumer range anxiety. And a focus on green energy is formalized. The comprehensive green electricity consumption ratio must reach 55 to 60% by 2030. This ensures that the massive growth in NEVs actually supports, rather than burdens, the push for renewable power.
And the safety metrics begin their climb toward that aerospace-level reliability.
Precisely. For technology managing megawatt power, safety is paramount. The charging accident risk rate must be controlled at less than or equal to 1 × 10⁸ per occurrence. And that's supported by AI-driven pre-warning accuracy reaching 98%. It's a significant operational target.
Shifting to hydrogen's 2030 goals.
The goal here is commercial viability for logistics. We're targeting 3,000 refueling or swapping stations. The price at the nozzle has to become highly competitive, reaching less than or equal to 25 CNY per kilogram of hydrogen. And crucially, the technology base for long haul gets established. Type IV density must hit 7.5 weight%, and liquid hydrogen systems have to achieve their initial industrialization and commercial demonstration.
Okay, moving into the midterm goals, 2031 to 2035. This is where the system really scales and intelligence becomes dominant. We're moving from pilot programs to large-scale market maturity.
This is the inflection point. V2G terminal penetration for new piles is set to skyrocket to over 50%. At this scale, the EV fleet is no longer just an optional resource. It becomes essential to grid stability.
And the capacity grows accordingly.
It grows tenfold. The daily adjustable capacity reaches 4 to 6 billion kilowatt hours, and the aggregate platform achieves a 90% response accuracy to grid commands.
This half-decade also locks in the extreme power future for charging.
Correct. Mega-charging standardization occurs here. Max output power reaches 1.5 to 2.5 megawatts, with voltage up to 1250 V. The consumer speed benchmark increases to providing 350+ kilometers in 5 minutes. And green energy consumption aims for 65 to 70%.
And the automated futuristic elements we talked about, they finally become common.
Right. Automation becomes a commercial standard. Automatic charging and swapping are widely deployed. Wireless charging finally matures into a commercial reality, achieving those high power and high efficiency targets. 22 kilowatts at over 94% efficiency.
And for hydrogen.
On the hydrogen side, we see 5,000 stations, the nozzle price dropping even further to less than or equal to 20 CNY per kilogram, and the heavy-duty liquid hydrogen truck commercial model becomes essentially mature. Hydrogen logistics solidifies its position as the backbone for long haul.
And finally, the long-term vision, 2036 to 2040, the absolute pinnacle of integration, efficiency, and safety. What's the strategic vision encapsulated in that final phrase? Parking means a pile. Traveling means extreme smart energy access.
The vision is a self-managing, intelligent vehicle energy road cloud infrastructure network that guarantees charging access and utilizes the vehicle's battery asset anywhere, anytime. The infrastructure anticipates and responds to your needs seamlessly.
The 2040 V2G metrics really confirm the EV fleet as a primary national power asset.
They do. V2G terminal penetration reaches over 80% of all new piles. The total regulating power capacity available to the grid hits 20 to 25 billion kilowatts, providing a daily adjustment volume of 8 to 12 billion kilowatt hours. This means the flexibility provided by aggregated consumer vehicles is a core mechanism for grid dispatch and stability.
And the ultimate benchmark for speed and power, that 3.75 megawatt goal.
Maximum single-gun output is projected to reach 3.75 megawatts at 1,250 volts and 3,000 amps. This extreme power level allows fast charging to provide 400-plus kilometers in 5 minutes. At this point, the performance gap between electric and fossil fuel refueling becomes completely negligible. NEV adoption becomes functionally superior in every single operational metric.
And the safety standards. We talked about aerospace levels earlier, but this is another level entirely.
It is. AI-enabled safety pre-warning accuracy is targeted at 99.9% or higher, and the charging accident risk rate is controlled at an astonishingly low level, less than or equal to 1 times 10 to the negative 9 per occurrence. That is a 10-fold improvement in safety assurance over the preceding phase. It reflects an engineered commitment to operational reliability that is usually reserved for the most critical national infrastructure.
And the hydrogen network completes the vision for 2040.
The network expands massively, aiming for 10,000 to 20,000 stations. The cost target stabilizes at that low 20 CNY per kilogram mark. And technologically, the Type 5e cylinder density reaches its peak goal of 9.2 weight%, ensuring maximum efficiency and range for the heavy-duty fleet. The entire dual-track system, electric for the mass market and hydrogen for the logistics core, is fully realized.
So to wrap this all up, if we're synthesizing the strategic conclusions of this massive roadmap, from that consultancy perspective we started with, we see a clear and intentional separation of focus, and it creates a really powerful synergy. The electric track handles the sheer volume and the grid integration. It's the low-carbon, intelligent backbone for cities and inter-city travel.
Correct. The core value of the charging network shifts from being just a fueling service to being a grid asset. And V2G is the core technology that executes this transformation. It makes the EV fleet an energy prosumer that's essential for managing high levels of intermittent renewable energy.
And the hydrogen track solves the critical pain points that electric solutions simply can't manage efficiently, at least not today.
Hydrogen is confirmed as the endgame solution for heavy-duty transport. Its strategic role is solving those hardcore challenges: extreme range, high payload, and rapid fueling. By focusing the R&D on high-density Type 4V and liquid hydrogen storage, the roadmap guarantees the economic viability of zero-emission heavy logistics.
This whole vision, it requires harmonizing standards across transportation, energy, architecture, cloud communication, and it demands developing those flexible market mechanisms for carbon and electricity trading that we discussed were missing in the last phase.
Absolutely. It demands constructing an entire innovation ecosystem. The technology itself is driving toward extreme precision, everything from that 4-centimeter localization target for charging robots to the high-powered DC-DC charger module efficiency of 98.5% or higher.
And all of this culminates in that near-zero failure safety standard, controlling the accident risk rate below 1 times 10 to the negative 9 per occurrence. This level of engineered perfection, it's usually reserved for aerospace components or nuclear operations, yet this is going to be a consumer-facing distributed power network that millions of people plug into every single day.
And that raises the final provocative thought for you, the learner. The technology is rapidly marching toward near-zero failure perfection and full autonomy. So what deeper societal, regulatory, and trust-based changes beyond just the technology and the standards will be required for society to fully accept, trust, and operate a consumer-facing energy network that's running on such extreme mission-critical standards? How do you engineer trust to match the engineering perfection?
A fascinating and massive challenge for the next 2 decades as the vehicle becomes a revenue-generating power asset. Thank you for joining us for this deep dive into the vehicle energy interaction and infrastructure technology roadmap.